Daniel Leibler from the University of Campus. Safety is for them. They will not come to stay here with us. So I will just show what they are doing. This is part of the storage system. The very competitive area that it's important to store hydrogen. Production is one thing, storage is another thing, utilization is another thing. But we are happy to know that will come already. So I will pass those slides in order to see. So this is hydrogen. A comparison between hydrogen gas and gasoline, and you see how powerful is hydrogen. It's much more than this is a clean fluid. When you burn it, you get water, not the two and like those two ones. Please. Okay. So this is the complex of how to hydrogen from sunlight, from water convection, wind energy, from electric generation, electrolysis. This is very good. Also, very high cost on this from fossil fuel doing the reform. It's very important because all the petrochemical industry or oil refineries to use hydrogen for energy using reform. This is a very adequate process because it produces a lot of CO2. So you next step is storage, you this. So this is how we store hydrogen, so you can put them in bottles or in systems like that you are going to do. Next step. So this is the fundamental question related with how we can store hydrogen inside this new material that we're going to see. So these are very applications of hydrogen, metallic hydrogen, that this material is like a sponge, metallic sponge that you introduce hydrogen over there. And so this material that the sponge is constructed could be magnetic or phosphor. That's some composite material like helium, hydrogen. So, for example, how traditional people store hydrogen, you can take a very high pressure and you compare, for example, the size of this grid storage system, liquid hydrogen, that's the fuel that takes the net from the moon, and slowly are going to see hydrates. These are materials that have a large capacity to absorb hydrogen. So that's the idea of the water. So hydrogen are still there. You see, Professor Hotchkiss, there are several words to have a car like that, not motorcycle or diesel one, but using fuel cell. And so that's the station technology. Nowadays there are several people. This is a question for Professor Hotchkiss. Okay. So how many patents you can have nowadays? Almost 2,000 patents with different fields of the area of biohydrogen. You see here metal, this hydrogen, you see how many patents are a very complicated area. So this is taking account of magnetic as a basic material as the area. So you can see how you put hydrogen inside this nanometer. The size of this spores of the hydrogen is spores. So this is the formula absorption of hydrogen is source of hydrogen, and you are going to use. You need to liberate the hydrogen. So these are all characteristics of the material that we develop into that compound. And I will not take much time on that, just to inform you that these are microphones from the material that was developed in that compound. Laminate. So these are for people that are like that, plus 5% iron. So just a rotation, they stay from the technology, they achieve it. And so they had 2 or 3 masterpieces from that, and they got a payment from the development. That's very important. So these are kinetic absorption solvent for taking different material, different they are okay. That's the number of the basics, the bottom. So the next one. So this is the Professor Walter contribution. Yes. Thank you. This is a very important point. I mentioned this in my talk. So we face this work here, what kind of industrial development. So the field has been used so much the best, like wood or coal, but this is no more. Nowadays, we are using a liquid fuel plant. It's a petroleum area. But the new area is the area of the gas fuels, like methane and hydrogen. So, of course, methane, when you burn methane, of course, you are going to have CO2 at the atmosphere. So that's why we break down methane from hydrogen. So this is the direction where it is to go. So we are in that direction. Some pictures just to show how this is much of the schedule of our colleagues. So this is 3 minutes. So it's prepared to be used in one reactor. So this one reactor was developed in Massachusetts, and this is another development of thermocrack, which was developed in the University of Federal Pernambuco by my colleagues. So this development are done. So this is the reduced carbon, that from this reduced carbon we can go to graphene, go for very expensive products. So this is another one important information. Maybe I had been discussing with Professor Maria Guijarro that we'll give a lecture on tomorrow instruction used by photolysis. She is one of the very specialized persons that works for the National Laboratory for Renewable Energy in the United States. Golden for that. And this was part of the data political supply. We developed the computational modeling showing that to produce hydrogen through the thermocracker system is feasible. That's important. Professor Maria Guimarães, we decided to exchange information on that. And so we are able to transform about 76% of the organic material that are in those effluents in carbon and hydrogen. So, the Professor Sávio doctoral thesis, he made not only the process development, but also he made the feasibility of this project. So, I mentioned to you, Professor Roberto, that this was part of the doctoral thesis also. So, okay. Professor Marwata. I will present the selection here to the system, especially in our population. So I look at it each under system, of course, so I can give you let me very quickly remind you that process of digestion is a well-established technology multiple function or a waste spectrum of different and causes associated with the energy. There are some things and two of these are relevant for the question. And the one is that biogas is not pure enough that for the rejection of fuel cells by part of the that means energy related processes such as the breathing. The other idea I would say is also particularly organic substance, CO2, and higher units that CO2 aerobic status. So, a novel technology could help to improve the situation based upon bioorganics. It is a large set of possible applications still under development. There are not any full-scale bioorganic systems in the world. But there is a lot of scientific and technical knowledge. The principle is that microorganisms can exchange electrons with solid electrons both for oxidation reaction and refusing reaction. Especially for the development of stuff with an autophysics microorganisms that can oxidize many different organic substances and deliver electrons to the external system. If you have an external electron receptor contact with the network, we have a positive situation which there is a kind of reaction that can be associated with production microorganisms. At the start, it was biological, and it was mostly non-biological reaction. And for reaction that can also cause mortality, or even can also cause mortality, you can keep that energy, so you can achieve the different power. If you look at the oxidation of organic substance and reaction time, you are doing that but you have a silver electron, so you can regulate the energy flow in this way. So research is interesting with many different approaches, many possible applications that you example good, the method of good, you can see that to feed this material that takes hydrogen and you reduce hydrogen to be sulfate, but in an excess of reducing power can reverse the flow level. So you can see here that if you polarize the electron at a negative dimension, you have proton flow with respect to the ionic flow, and all these proton flow is converted into by using C2. This is the ionic flow, and this is ionic fluid. You can see after all the hours of hydrogen production in the is going on, that means that the reaction is not even H2 is activated and this is here is too much shows the oxidation of H2 the oxidation that is increased because we need resistance within the hydrogen against the concentration level. It also is interesting here that during time you continue after the release your objective is on the electron is not that means balancing and forward you can the electron. But this is for just to give an example of the application
concentration of in these general fixed approaches, we will try to convert not to reduction, but to so to use this approach by creating the digestive or COP, organic matter, CO2, for proteins are produced to capture there is a flow of diet, flow and catalysis. These are passive. The problem changes the way and those HQ and electrons are used to reduce the net production needed. If you are using an ion electron, the flow of electrons through the but the active transfer will do it the opposite direction, which minus or beta minus or beta. So by using this, you have an efficient method, not only to produce energy, but also to remove nitrogen or to remove carbonate that we use to improve the quality of digestive and the fiber. So I mentioned yesterday something about these two systems, but today I will just give you preliminary insight using a two-channel something happening both ways. If you have one intermediate channel you use two memories, you have that passing between the protein and ammonia, and on the other side, transport of other two ions, beta and depending on the information, you can have a stimulation of both to purification of virus, treatment, and accumulation to recover ammonia and beta treatment until later. Experiments with this concept. Okay. It was a continuous flow of each channel. I talked about the one with a partner. There was a synthetic solution with many characters to the panel. There was a synthetic mixture of nitrogen and CO2 fluid, the catalyst increasing of the virus. It's a lab for certain reasons, and then the relationship to the brain. These are our conditions. There's no time to move into detail, but I like to say that it's a fresh one expectation of this. There is not any other reason than just this channel that is the only channel between the disaster. So, to give you an idea, about flow today, influence the ethnicity, which state and the nuance of it, you can see that at the end of the removal and effect, the index is focused and even a little bit acid. That means that also almost energetic reactions are going on. So the CO2 is transported in bonds, methane, and acetic acid. That some parameters that we can use to just analyze your system, the velocity efficiency, 65%, and the only efficiency is really high. That means that the CO2 was disconverted into electrons, and this is the rate of production of methane, and you can see here that the caloric efficiency is also good. This means that most 70% of the electrons are being released are devoted to methane, so the global efficiency is 75%. This means that 75% of the different potential electrons are being devoted to methane or acid. Most important is that very little production of water systems in the effort from the end, so there is low flash production. Just to give you some idea about balances, so we can see here the balance would be 100%. The total CO2 is we can use 100%, almost 60% using 6% into marketing, 20% into finance, we lose 16% also into other products are not directly targeted. Another important use about American is the narrative is entering the system, and you can see that this narrative is concentrated into the carrot and relation chamber is from about 60 to 300, so it's concentrated 5 times that is way to spin out the nitrogen from the activation chamber. This is about, you can see that the recovery is very good, the efficiency of the water was not so good, most of the ammonia was removed to this speed. So because the program is going on, the ammonia is forming is there. Higher concentration, like in the also for bicarbonate, you see this is flowing, the influence flow of bicarbonate is quite more concentrated to the activation chamber. Anyway, you don't have any different concentration in the activation, and the kind of that makes the selective memory is not operating so good, so you don't have any contribution from higher transport. So the mechanism is that bicarbonate is driven to absorption. CO2 is actually flowing in the system. It is absorbed as bicarbonate. Bicarbonate is working to methane to acetate 50%. But most of this is flowing through the membrane to the activation chamber and then spewed out high concentration. So something in some way sequestered into the system. Finally, which is the energy balance is how much of the energy you can recover in terms of methane with respect to the energy spent with the apparatus working. This is going to be too low, 42%, that we spend too much energy. But I want to stress that in this part, we didn't take account of the cost of support to be absorbed because for free in our and so the balance you should improve and so at the end we are demonstrating and continue to condition that each other by government that simultaneously the CO2 can transfer to the with ammonia and carbonate yet so just the first experiment, the recovery more or less of food that the chemical was very good, but the energy flow was not good enough. Anyway, there is the energy from the CO2 absorption scheme. There is improvement to be done about the efficiency of ammonia and good recovery, and this probably due to the amount and the number are too low that we are good to this. So we are now reading the economic potential. The economic potential, we were working was very high just to have a reference. By the treating effect, the economic potential will reference from the energy. Of course, it will be the most selective change number and based on this, we would be able to characterize all points of this population and give a model for our system. The next action, of course, would be to feed another channel with influence with the physical recovery and hopefully to reality real time in a scale that or hopefully in this project. Thank you very much.
Thank you very much. Thank you, Professor. So I will now have the pleasure to give Professor Sebastian a speak. Please.
breadcrumbs are those bread brought inside into the nutrient solution. That's the manipulation here. Next here, there's a picture of these equipment here for small hydrogen reactor or buffering storage tank. Here for bigger methane reactor. Here we work on the scale of 10 liters for hydrogen production and methane production around about 50 liters. Monitoring these reactors or the temperature, the pH value, the gas production, efficiency and output, so the hydraulic retention time is important. Finally, and we do of course the analysis of liquids, COD, organic acids, the dissolved oxygen content, the concentration of nitrogen, and the end. So summary about this with my colleague PhD thesis that the digestion lab would be enough to 70 degrees and causes a sustainable sinking material for hydrogen production. If we bring up the organic load rate, the H2 concentration brings up the H2 goes down. This should can be repaired as a vegetable. For example, the hydrogen production is possible at any temperatures that are higher than 60 degrees. Because the consuming temperature would be higher, because Bashir had shown that a combination of hydrogen and methane production is the option. We want to divide those stages quickly to not get different materials in the other reactor. And the organic load rate is CH4 stage is very low. Here I just want to show you a new project that's quite running for some months, and so we could build up a new reactor on the wastewater treatment plant with here directly input. We put there waste sugar and mixture of waste and sugar. Here we have our hydrogen bioreactor and the size of 100 liters. We have a special gas treatment after the bioreactor, and then we use the hydrogen in a fuel cell and produce their electric energy. The output of our bioreactor, there are two opportunities to use it to bring it to the fermentation or to bring it into the multiple application plant to get out CH4 and also the different parts used as carbon salts for the denitrification in the wastewater. So here's some of the illustration of the proposal setup. We have here the reactor volume of 100 liters, the hydraulic retention time 24 hours. For substrate is there a solution of sugar and graphene. The expected gas quantity that we have in our reactors that are around about 20 liters. We got the gas quantity between 40 up to 60% of the hydrogen, and we use it in fuel cell. Here is something scale up the overview of the different components we use there. I think the main part is the reactor. Then we have the different pumping, we have different flow meters and pumping stages for the nutrient solution and for circulation inside, and it's all completely controlled by our mechanical. Thank you for your attention.
Thank you. Als eerste was de grootste product.
Yeah, good morning. Good morning, ladies and gentlemen. I think I can make here a look of the far end of the process chain that is being discussed this morning. I'm not a real expert in chemistry or biotechnology, but my field is vehicle design. Vehicle design includes vehicle technologies and fuels for vehicles. That's the reason why we are very much interested in the way how to produce hydrogen, how to use this hydrogen in modern green mobility. So for all of you who are interested in this field and like to know a little bit more about the farming or legal application, I'd like to recommend you to listen to my talk, which is on the agenda for this afternoon. And what I'm going to do right now is just to take 3 or 4 slides out of the presentation, which are in content with the subject we have discussed this morning. So this is a picture which I took and I optimized a little bit and added some new articles just to show how complicated and how differentiated the world of fuels will be in the future. So if you see here, we have a very conventional line. The path which goes from fossil sources to liquid fuels and the internal combustion engine. This is what is good for maybe 80 or 90% of cars today. We have now, of course, another very interesting task. This is this one from natural gas or from coal. This is sometimes the case in China, and it goes via gasification and the so-called Fischer-Tropsch synthesis also into the liquid fuels, and it can be used in internal combustion engines or more and more in hybrid drivetrains. Now comes in the biomass. And you see biomass is in Europe, in Germany, mainly based on grain. In other countries on ethanol. In Brazil, you know better than I do that this comes from the sugarcane production wood. All this can be used again to produce liquid fuels, and you know what the ethanol story, especially for this part of the world, means. Biomass can also be used as biogas in the methane production. This is a very interesting part because it combines the use of CH4 methane in conventional engines, thus reducing about 25% of CO2 emission compared to conventional gasoline. Or if you use biogas, then you have, of course, balance with a sustainable source, and you have a better design. So the use of CH4 will play, I think, a better or more prominent role in the future. I thought the sheet was okay, so I have to start again to show the picture. Because this is very important, and I think this is what you and me will interest more when we want to give to us so-called sustainable energy. So combined with hydro energy, also including biogas, which goes now directly into electricity. And this is what we are discussing right now and intensively, mainly in Europe, as you know, the electricity to bring it in plug-in hybrids or in pure battery electric vehicles. So that is the reason why we need electricity, and why we should, of course, use these sources for. Now, finally comes hydrogen, and hydrogen is, of course, done by electrolyzers today. It's coming from steam reforming. We want to have it in electrolyzer process or in other processes. And that's the reason why I hope that you, with your project results in the future can additionally show some paths for the hydrogen production for the future. When I said I added this picture, I show you this. This new, for me, it's new blue line which goes from hydrogen, taking into account the methanization of the methane, and again have here a source of storage for the fluctuant energy by electrolyzers, by hydrogen production combined with the utilization process to produce CH2 for mobile applications or for any other. So that's the one picture, and then I can show you this. I will show it this afternoon again, a little bit more detail, but I'd like to show it for you right now, because it gives for me the indication that the future is really differentiated, and that new pathways and new technologies like those we are discussing this morning fit very well in this interesting world. Talking about hydrogen, you all know that hydrogen today is ready for serious applications with systems similar to this. You know, it's electric drivetrain, so the electric engine needs electricity. The electricity is generated with the fuel cell stack, and the fuel cell has to be stored. Today, up-to-date technology for storage is high pressure storage with several hundred bars pressure. And that's ready for use, and all these sort of hydrogen cars were also already tested in the whole plant tests for my institute, by the way. So I really can tell you they are suitable for normal drivetrain processes. They are technologically sound, but of course they are a little bit expensive, so cost is an issue, as well as the infrastructure of hydrogen route. Well, this is the way how the hydrogen is generated in the fuel cell reaction. I don't go into details anymore. I just like to show you this as a last example of what we are doing, or what the background for my work is. We see here an up-to-date project where we started to integrate the fuel cell as a range extender into an electric vehicle, into a battery electric vehicle. We do this together with the Daimler. You see here Daimler Smart. This is a normal electric Smart. This Smart is good for 80, 90 kilometers electric drive, so that's not so very much. And we decided to install fuel cell range extender technology to double the range for the electric engine. This project was discussed, or a similar project was discussed for some years already, when we started to talk about the process change from hydrogen, maybe biomass-based generated here in Brazil and stored in a hydrogen metal hybrid storage. You mentioned Professor Boda from São Paulo, and then of course used in such cars or similar cars here in Brazil or wherever in the world. So this was the idea. This project idea didn't show up so quickly. So we went into this application where we said, well, we want to have a range extended technology based on hydrogen for electric. This is what we are doing right now. And again, I can imagine that sometimes, I don't know, in the very far future, Brazil can produce hydrogen in a different way and can apply such cars or applications for the mobility. So that's all what I have to say right now.
Thank you very much, Professor. We still have about 10 minutes. Then, if someone wants to make some questions to one of the speakers, I would like to please to address this.